Good afternoon all. So before going to the actual fuzzy logic, we'll see the classical sets and its operations. Then we'll go for the fuzzy sets and its operations. So by understanding these classical sets and its operation, then it will be easy for the fuzzy sets and its operation. So what is fuzzy? All of you know that logic, Boolean logic, right? In a similar way, here we will learn the fuzzy logic. So in Boolean logic, you'll get only two states, either it is 0 or 1. That is nothing but either yes or no. There is no intermediate option. But in fuzzy logic, you'll get the intermediate options also. That is nothing but 0, 0 0.1, 0 0.2, 0 0.25 and so on up to 1. From 0 to 1, what are the number possibilities are there? All the numbers can be represented in the fuzzy logic. So whereas in Boolean only we can represent with the 0 or 1. A good example for this fuzzy logic is, so what is the state of a cup of tea means? We can say either it is cold or it is hot. In Boolean means we can say either it is cold or it is hot. But if you want to represent the same thing in fuzzy logic means it is too cold, it is too hot, it is moderate cold, it is medium hot. There are multiple ways to represent that state of the tea. So that is fuzzy logic. So we can represent that hot, cold, mild cold, moderate cold, and so in many ways, right? So like how we have seen with 0, 1, in between 0 and 1, we have many numbers. So that is to represent those numbers, we need to use a fuzzy logic. So first we'll see the classical sets and its operations. So what is classical sets? We consider a classical set where capital X denotes the universe of discourse or universal sets. Let us represent that capital X with the universe of discourse or universal sets. That means entire set is called the universal set, or all the sets, combination of all the sets is nothing but universal set or universal discourse. So the individual elements in the universal X will be denoted as a small x. The features of these elements in universe of discourse, that is capital X, can be either it can be continuous or infinite number, it can be discrete and finite number. Let us take a simple example. Even if you consider alphabets, there are 26 alphabets. All 26 alphabets belongs to one set, means that is one set. Again, small alphabets, that is another set. Together, small alphabets 26 set and capital alphabets 26 elements, that is nothing but elements are letters, so belongs to another set. So if you mix all those alphabets and if you keep it in another set, and if you consider that as capital X, that capital X is nothing but universal sets or universe of discourse. So the features of that elements in that universe of discourse may be continuous, infinite, means there may be continuous numbers. If it is continuous numbers, means you can represent or you can have infinite numbers. If it is discrete and finite number, there may be 1, 5, 10. Below 10 numbers belongs to one set. From 10 to 20 belongs to one set. Likewise, you can give finite numbers also, or discrete numbers also, even 1.1, 1.2, likewise also. So all these individual numbers can be anything. If you take the realistic example, the temperature, speed, all those belongs to these small x values. That may be anything, right? Speed can vary from 0 to 1500 rpm, means it can be 1400, 1300, 1200, even 0 or 1500 rpm also, if you want to apply the same fuzzy logic to the speed control of motors. You can take any intermediate value, even 1400.5 also you can take by using this fuzzy logic. You can use any value in between 0 to 1500. So that's why the features of the elements in that units of discourse is continuous and infinite, as well as discrete and finite also. So what is the choice of universe? The total number of elements in a universe, capital X, is called its cardinal number and is denoted by neta x. So how many number of elements are there? That number is equal to the cardinal number. So cardinal number is represented with the neta x. So generally we have two type of universe, units of discourse, right? One is discrete universe, another one is continuous universe. In the discrete universe, it is composed of the countable finite collection of elements, and it has finite cardinal number. So there are finite numbers, means obviously your cardinal number of elements in the universe of discourse is finite number only. If it is continuous universe, means it consists of uncountable or infinite collection of elements. Thus, it has infinite cardinal number. And we will see this with example. What is power set? The collection of elements in the universe are called as sets. So all the collection of elements in the universe are called as sets. That means all the sets. Like I told you, you may have a few numbers can be treated as one set, another set of numbers can be treated as another set, likewise. And the collection of all these elements in the elements within the sets are called the subsets. You can make sets, you can make another subset also. Already you might have studied all these things in the mathematics also. So the collection of all the elements in the universe is called whole set. If you consider all the elements, if you take into consideration of all the elements, then that is called the whole set, which is nothing but it is analogous to the sudden event. Particular sudden event, we will consider that as sudden event. In sudden event or whole set consists of all elements. If there are no elements in particular set, then what is it called? It is called null set. The null set, which is represented with pi, which has no element, or no event in that particular set, which is analogous to the impossible event. Impossible event means there are no events. That is called the null set or pi set, which is represented with the pi. The power set constitutes all possible sets of X, that is nothing but capital X, okay, units of discourse, and is denoted by the P of X. Here P of X is nothing but power set, so which consists of all possible sets of units of discourse capital X. That means including with null set to whole set. From null set to whole set, what are all possible sets? That is nothing but power set. See with that example, what is power set, what is cardinal number, so what is cardinal number of power set, all these things we'll see with this example. Let us consider that universe comprised of three elements. The units of discourse represented with capital X, which is equal to 1, 2, 3. Three numbers are there. Find the cardinal number, power set, and cardinality of power set. So coming to the solution for this, to find out that cardinal number, what is cardinal number? Cardinal number is nothing but the number of elements in the defined set. The defined set is nothing but capital X, which has only three numbers. That's why the defined set X consists of three elements, which are nothing but 1, 2 and 3. Therefore, the cardinal number, which is represented with neta X, is equal to 3. Cardinal number is equal to 3. The power set consists of all possible sets of x, right? What is power set? All possible sets of x. What are the possible sets of given x units of discourse? What are the possible events means or possible sets means? We'll see. It is represented as all the possible events which are nothing but there is a chance of null set, there is a chance of only 1 with one set, 2 with one set, 3 there is a combination of 1 2 1 3 2 3 1 2 3 also. So this is called the power set. All possible events of universal discourse is nothing but power set. P of x is equal to all possible events of the three elements. So what is the cardinality of that power set? That is nothing but neta of P of x. Neta of x already we have seen. Neta x we have already seen, which is equal to 3. To find out that neta px, P of x, which is nothing but you can find out by using the formula 2 power neta x. What is neta x? Cardinality of this universe of discourse. There are three elements. Cardinality of that universe of discourse is nothing but 3. So 2 power 3, which is equal to 8. Cardinality of the power set is given by 2 power neta x, which is equal to 8. Otherwise you can count that all possible sets in the units of discourse also. The power set. How many possible events are there in that power set? There is pi 1 2 3 1 2 1 3 2 3 1 2 3. If you count all those events or sets, that is equal to 8. That can be found out by using the formula 2 power neta x. Here neta x already we found. Neta x is nothing but 3. That only substitute here. Then you'll get 2 power 3 is equal to 8. If you have 4, even this set may not be with the numbers also. It can be with the alphabets also. Let us consider A, B, C, D is one set means. What is the cardinality of that A, B, C, D set means? How many letters are there in that? 4. Cardinality of that set is nothing but 4. What is the cardinality of the power set for that A, B, C, D units of discourse means 2 power 4, which is equal to 16 possible combinations you will get it, which is equal to power set P of x. Okay, like that you can find out the cardinality of the cardinality number, cardinality of the power set P of x. So if you see that classical set operations, what are the possible operations with that classical set means? There is a union operation, intersection operation, complement operation, difference operation. We'll see one by one. If coming to the union operation, let us consider two sets. One is set A, another one is set B. The union of two classical sets A and B is denoted as A union B. A union B is the union of two classical sets A and B. It represents all the elements in the universe that contains in either the set A or the set B or both set A and set B. So by somehow, if you take one element that either it belongs to A, B or the common portion of A and B also. So that is nothing but A union B. This operation is similar to the logical OR. We have to add both of them. It is represented in the set theoretic form as follows, like A union B is equal to X such that X belongs to A or X belongs to B. So your small x element in A union B, it belongs to either A or it belongs to either B, but it should be within that A and B only. So if you see that Venn diagram for A union B, so that entire box represents the units of discourse. That may be capital X or you can denote with some other a letter that may be Z. So within that two circles are there, right? One circle is A set, another circle is B set. If it is A union B means from A circle, B circle and the intersection portion also. So that hatched portion represent the A union B. I hope you understood. So next, intersection. The intersection of two classical sets A and B is denoted by the A intersection B. It is the set of all the elements that belongs to A and B. That means the elements which belongs to both A and B is nothing but A intersection B. Whatever the element, if it belongs to both A as well as B, that portion only we need to consider, that element only A intersection B part. So that can be represented in the theoretic form. A intersection B is equal to X such that X belongs to A and X belongs to B also. So if you see that Venn diagram, where do you get that equation? X should belongs to A as well as X should belongs to B also. Only that common portion which is hatched with the green line. So that belongs to the A intersection B portion. Venn diagram shows that A intersection B. So that hatched portion is nothing but A intersection B part. So that hatched portion is nothing but, in that portion whatever the elements are there, those elements are belongs to both A set as well as the B set. That is the intersection portion. Next, complement. The complement of a set is the set of all the elements which are in universe of discourse Z but not in A. If you see the equation, A complement, above one line is there, right, that represents the A complement, or A superscript C also you can represent. So here I have used A complement, which is equal to X such that X does not belongs to A but X is belongs to the Z. Here Z is nothing but universe of discourse, so that is nothing but rectangle box. So here X should not belongs to that complemented set. For example, if you see that Venn diagram for A complement, that circle represents the set A. If you want to find out the complement of that A set, you exclude that A set and the remaining all the portion in the universe of discourse which is hatched with the green portion is belongs to the A complement. Other than that, set A in the universe of discourse belongs to the complement of A. Okay. Then difference. The difference of set A and set B is nothing but A minus B. The set of all the elements which are in set A but not in set B. Difference means all the elements which are belongs to or which are in set A, which belongs to set A only, not belongs to the set B. So the theoretic equation A vertical line B or A minus B can be represented like X such that X belongs to A and X does not belongs to B. X belongs to A and X does not belongs to B. So if you see the Venn diagram for that difference, so how can you hash that portion? X is set, X belongs to A only. There are two sets, A and B set, right? X belongs to A, but X should not belongs to B means, X does not belongs to B means, so that common portion also should not be included in that hash portion, because there B also included, right, in that common portion, intersection portion. That's why by excluding that B, as well as the intersection portion of A and B, the leftover A set is belongs to the A minus B. in the units of discourse. If you want to do the same thing for B minus A, means you need to exclude the complete A set, including the intersection portion, only the right side B portion only, B minus A likewise. So these are the classical sets and its operations. Thank you.